Now let's talk about the reversible work in an open system exchanging heat only with the surroundings. Alright, now for this let us consider an open system which is exchanging energy only with the surroundings at constant temperature. So let us say this is the surroundings and this is the open system. Now the conditions of surroundings are pressure P0 and temperature T0. Now let us say a mass dm1, it enters the system at state 1. So this is the entry to the system, and let us say the state is state 1. Okay, so this is the mass that enters. Let's write it here. Now let us say mass dm2, it exits the system at state 2. So this is the exit and this is the state 2. So this is the mass which is at exit. Okay, now an amount of heat dq is absorbed by the system. So this is the amount of heat that is being absorbed by the system, and an amount of work dw is delivered by the system. Okay, so if you look at this, this is the amount of work that is delivered by the system. So dq is the heat absorbed by the system. Okay, and dw is the work output by the system. Okay, so these are some parameters which define the system, and this is the control volume of the system. Okay, now the energy of the system, or you can say the control volume, because there is some energy exchange from the system to the surroundings or between the system and the surroundings, there is a change in the energy of the system. So the energy of the system or of the control volume, it changes by an amount dE, and let's put a symbol sigma. So this sigma is symbolizing a change in the energy of the system or the control volume. That is all it symbolizes, nothing else. So this is the change in the energy of the system, or the control volume. Okay, so if you apply the first law on the entry, exit and the heat interaction in the form of dq and the work interaction in the form of dw with this system, let's apply the first law on this and let's write it down. So the first law, let's write down the energy at inlet. So the energy which is coming in the system, one of those energy is the heat. So you write down dq plus the energy that is coming via the entry with the mass flow dm1. So you will have dm1 into, you will have the enthalpy h1 plus the kinetic energy v1 square by 2 plus the potential energy, so g into z1. So you will write down dm1 into h1 plus v1 square by 2 plus g into z1. Okay, now there is some energy which is going out of the system at exit, so that is dm2 into h2 plus v2 square by 2 plus g into z2. So you will write down minus, because this is going out of the system, dm2 into h2 plus v2 square by 2 plus g into z2. And then work is also going out of the system. This total, or you can say this net energy interaction, gives rise, or it changes the energy of the system. Now dE sigma, this is basically the change in energy of the system, which is given as d into u plus mv square by 2 plus m into g into z, and this is for the control volume, which is represented by the symbol sigma. Okay, so this can be further written as d of u plus mv square by 2 plus mgz, and this is for the value sigma. Okay, now let's go back to the diagram and see that there is a temperature difference between the control volume and the surroundings. The control volume is at the temperature T and the surroundings are at temperature T naught. So there is a finite temperature difference. Okay, now in order to have maximum work out of this process, the process has to be entirely reversible. So to make the heat transfer process reversible, let's assume a reversible heat engine. So this is a reversible heat engine, okay, that is operating between the two temperature limits, that is between T naught and between T. Okay, so this is to make the heat flow or the heat transfer process completely reversible, which will give you the maximum amount of work output. Now again, the temperature of the fluid in the control volume may be different at different points. So let us say the heat transfer occurs at points of the control surface which is at temperature T. So let's take this much area which is at temperature T. You might have a different temperature at this point. You might have a different temperature at this point. So let's take the temperature at this region to be T. Now this is an infinitesimal reversible process for which the amount of heat dq naught, it is absorbed from the surroundings, okay, or you can say absorbed by the reversible engine, okay, and an amount of heat dq is rejected by the engine reversibly to the system which is at temperature T, and an amount of work dwc, it is done by the engine. Now for a reversible engine, if I might write down, let's bring it down. So for a reversible engine, alright, you can say that dq naught upon T naught, this is equal to dq upon T. That is, the entropy change has to be the same. And if you look at the value for dwc, this is equal to dq naught minus dq. So this will be equal to dwc is equal to dq naught minus dq. Alright, so if you find out the value of dq naught from this particular equation, I will get dq into T naught upon T. So let's put this value over here, which is equal to dq naught, and I will get dq into T naught by T minus dq. So the value of dwc, this becomes equal to dq into T naught by T minus 1. So this is the value of work output from a reversible heat engine, which is exchanging heat between the surroundings at T naught and an infinitesimal area of the system or region of the system at temperature T. Alright, so this is what the value of dwc will be. Now the work dwc is always positive. This is always a positive work, and it is independent of the direction of heat flow. Now when you have T naught higher than T, then the heat will be flowing from surroundings to system, okay, and when the value of T naught is less than T, then the heat will flow in the reverse direction, that is from system to surroundings. Now since the process is reversible, the entropy change of the system will be equal to the net entropy transfer. Right, so this is again a very important concept we read about in the second law in entropy, that for a reversible process, alright, the entropy generation is 0. There is no entropy generation in the system. Okay, so the entropy change of the system is equal to the net entropy transfer. So entropy change of the system is equal to net entropy transfer. Alright, and this is equal to 0. Now, the entropy change of the system is, let us say, ds. Okay, so the entropy change of the system is ds. Now, the net entropy transfer, you have some heat transfer, isn't it? So due to the heat transfer, there will be a entropy change. So this is equal to dq by t, which is the entropy change due to the heat transfer, and then you have some entropy transfer due to the mass, because there is some mass which is flowing in and out of the system. So you will have plus dm1 into s1 minus dm2 into s2. So this part over here is the entropy transfer with heat. So this is the entropy transfer with heat, alright, and this part is the entropy transfer with mass. So this is entropy transfer with mass. Okay, so let's rearrange this equation a bit, and I can have dq upon t is equal to ds minus dm1 s1 plus dm2 into s2. So let's put this in a green box. Now, the maximum work is equal to the sum of the system work and the work out of the reversible engine E. So if you look at this diagram again, the maximum work is basically the sum of this plus this. So this coming out would be dw max, which is equal to dwc plus dw, that is the work coming out of the system. So that is equal to dw max, this is equal to dwc plus dw. Now this is the reversible work, because for work to be maximum it has to be a reversible work. Now if you look at this particular equation, I have the value for dwc. So let's put in the value of dwc in this particular equation. So we will have dw max is equal to, so the value for this is, you have dq into t naught by t minus 1 plus dw. Okay, so if you substitute the value of dw from this equation, that is the steady flow energy equation, from this equation, let's substitute the value for dw over here. Okay, so from here let's find the value for dw and put that value of dw in this equation. So you would have dw max, it will be a long equation, is equal to dq into t naught by t minus 1 plus the value for dw. This is equal to dq into, not into, but plus dm1 into H1 plus V1 square by 2 plus G into Z1 minus dm2 into H2 plus V2 square by 2 plus GZ2 minus d into u plus mv square by 2 plus mgz, and this is for the control volume. Okay, so this will be the equation that you get. Okay, now in this equation you can easily strike off this part and this part. Alright, and you can then substitute the value of dq into dq upon t. Now the value of dq upon t, what is the value of dq upon t? Let's have a look at that. So the is this. So this is the value of dq upon t, that is ds minus dm1s1 plus dm2s2. Alright, so this is the value. So you can put it over here. So you can say it becomes equal to this is T naught. So T naught will come outside into, you'll have ds. Okay, you'll have ds minus dm1 s1 plus dm2 s2 plus all these terms. So that is the value of the maximum work that comes out of an open system which is exchanging heat only with the surroundings at temperature T0 and P0. So I hope you understood this expression. So at the end, let me just write down the final expression that you would get after manipulating all the values, and that is what you need to remember. So that would be equal to dW max is equal to dm1 into h1 minus T0 s1 plus v1 square by 2 plus gz1. So this is the total energy which comes out or which comes into the system with the mass inflow of dm1 minus dm2, which is into h2 minus T0 into s2 plus v2 square by 2 plus g into z2 minus d of u plus mv square by 2 plus mg z, and this is for the control volume sigma. So this is the final expression of the maximum work that is obtained of an open system which exchanges heat only with the surroundings at T0 and P0. So you should note down this equation, because we'll use this in the next video in which we talk about the reversible work in a steady flow process.